Right, well, hello, welcome. This is a Houdini tutorial for, this is not highly detailed in terms of what these instances are, but this is supposed to be a vesicle fusing with a cellular membrane. So this is what we're trying to achieve here. And as you can sort of see from the fact that I've highlighted this in two different colours, the nice thing about this approach is that you get persistence of the lipids in space. Because I tried to do this in Blender about a year ago, and the general approach that you might take, and if you've tried this is perhaps the way you've tried to do it, is that you have an underlying geometry that gives you these nice sort of blobby shapes, and I'm sure there are better ways to achieve this than how I've done it, but this is my first approach, kind of thought of how to do it. And then once you have that mesh, what you would do is you'd scatter points on this surface, and then later you can instance your lipids onto those points. Now, the point that I got to in Blender was essentially this, where you have these points, but if you roll this forward, you can see that the points change their positions on each frame, and that's because your base geometry is changing on each frame. So the scatter node just generates a new scatter pattern because of that changing geometry. But what my approach here avoids is that sort of jitteriness. And the way that I'm achieving that is using an inbuilt solver. There are some custom things going on within this solver. I'll get back to this later. Obviously, it might look a little bit scary, but it's not too bad. Most of it is relying on the inbuilt solver of Houdini, the grains solver. But the advantage of this approach. What's going on here? The advantage of this approach is if you choose one of these lipids to look at whilst I play the animation forwards, you can see, because we're using that particle solver, that these lipids kind of push each other out of the way, and we can get them to conform quite nicely with a few bit of vector mathematics tricks. But this is the sort of result that you'll get if you follow along this tutorial. So hopefully the motivation for this tutorial is clear. And the way that I'm going to do it is that I already have the nodes set up, but I'm going to rebuild the entire thing piece by piece so that I can sort of discuss with you like what each part is doing. So I'll start off by cheating a little bit and just copying these two things out. But what I'm starting off with is a box which will become the membrane of the cell, or the flat membrane, if you will. And I've just chosen these sizes here, 8 by 5 by 8, and then I've just lowered that down in the y-axis, just so that that's at y equals 0. And so the other thing that we want is a sphere. Again, I've set them to these values just based on what you want. You can set your values differently, but the main thing here is that at keyframe 1, what I've done is I've gone into keyframes, set the keyframe to be above the box, and then in this particular animation by keyframe 120, it's gone down, so it merges, or it goes inside of this box, and that's important for that merging that we will see later. So from this point, what we want to do is convert these polygons into volumes, because that's how I'm going to generate the nice blobby shape of the vesicle fusion. So what I want is VDB from polygons. Drop that down. The default values are fine for this. So what you can do, you can merge these first, but I found that it works slightly better if you convert each of them into a volume first. or no, so what we want to do now is merge them. So VDB merge, and then just drag those down into there, and voila, we have voxels. So I guess what we could do here now is that if we convert this back to polygons, they will merge into one geometry. So let's have a look at what that looks like, and I'm going to use a convert VDB to do that. And what we want to do is convert it to polygons. So you can see if you do this, then well, it kind of merges. That's fine. What I will just add on to the end here so that we can sort of see what's going on underneath is this blast node, and what that is doing is just getting rid of all of the box that we don't need. And the way that I achieve that is that you're working on points, and then if you put this expression on here, it's going to blast any point that has a y position, so this vertical axis here, less than 0.1. So hopefully that makes sense. And then you can see here from underneath, it's just become one mesh, right? But I don't like how jagged this is, and also it only merges when it's really close. So what we want to do, just move those down a bit, is do a little bit more trickery in here. So I'm going to drop down a VDB smooth. Maybe let's try this one. I'm not entirely sure on the differences between the SDF and the VDB smooth because I only learned Houdini about a month or two ago. So you'll probably see lots of odd things in this tutorial that you'll think like, what's this guy doing? But just bear with me, and hopefully the core kind of things are useful to you. But what we can do here is we can play around with how much smoothing is going on, and what this will do is if we bring that up, bring it down a little bit more, you can see what playing around with these iterations kind of changes what shape that we get out of this. Now if I just go to here, this is the type of thing that you're going to get. What I prefer generally, well actually I haven't tried these other ones, don't know what these ones do, these different methods. These might be useful, but they don't seem to really do a good job. What I tend to do is use Gaussian. It's not looking very good, is it? There we go. You know what? This is this is not looking very good. So let's just do that. First order winding, fifth order. That looks interesting. That's quite nice. I quite like that actually. In the previous version I've just used VDB smooth and it seems to do a slightly different job. It seems to have a few more options. So I'm gonna, you know what? I'm gonna stick with this, and I'm gonna see if it completely messes up the stuff later. In which case, I'll just come back and change that. But essentially, that's what we're looking for. Is that kind of blobby fusing type shape, right? And the last thing that we can do is add some noise into this. So I'm just going to copy this over because I don't want to trial and error the parameters in here again. But I'm using an attribute noise. It's going to be working on the points in this geometry. And what I want to also do is do noise along the vector. Because if we don't do that, it looks a bit So noise along vector, along the normal just means that whatever the normals of each point is just going to push it in that direction, and that looks just nicer. It gives you a better result. Play around with the amplitude. I think what won't be by default is this one. Maybe it is, but I've put it on 0 centered just so that it's pushing up and down equally. And you can animate this as well. I've put it at this. Probably element size I played around with. If you make it really small, then you get lots of noise. You can make it look like that. But I found this value to be good. I don't think I played around with these fractal values, but compare it to what you're looking at in Houdini and go from there. But with that, essentially what we have, I guess this is kind of taking a little bit longer to compute than the other approach that I used, but I mean it's still fairly good in terms of computational time, it looks like. So I'll leave it at that. Let's just kind of organize this, make it look a bit nice. Just be a bit perfectionist about the whole thing, and let's put a box in here and underlying mesh just to kind of organize it, and then maybe let's drop down a null in case we want to. Yeah, I've called it base geometry here. I'll just call it base mesh here, just so that we have something that we can look to or potentially use if we want to take it out of this geometry later. Okay, so I'll take a little break and then I will come back to this second part here. Right, so I've just had a few days between making the first part of this tutorial and this little jump that you will have seen, just because I've been a bit busy. But one thing I wanted to add in here, because coming back to this, I sort of noticed that it does take a bit of time to calculate this underlying mesh. I'm sure there's better ways that you can do it, but for now, what I've added in is a file cache node, and that just saves all of the outputs from this to the disk. So instead of calculating every frame, you just have access to it straight away. So if you do drop one of these down, just name a folder that you want to save it in, give it a file name, and then press save to disk. And then you'll notice that this calculates, well, it doesn't calculate, it just it works faster because it's already saved. So yeah, we have the underlying mesh. The next step that we want to work on is putting some particles on this mesh and then moving them around. And the first thing to drop down, the way that we can populate this mesh with points, is by using a scatter node. And I ended up using 10,000 points. And then after this point, I actually worked on giving these particles a certain colour. So this isn't an absolutely necessary part of it, but I think it's quite a nice thing to do. If we drop a colour node down, we can see that this gives it different colours that we select. But what I want is to actually colour this vesicle differently from these points down here. And the way that I can do that is by first dropping down an attribute wrangle. And then I'm going to get out of this the y coordinates of the points. So if I make a float, which is f at, and then color position, and that's going to be based on the position and specifically the y coordinate. So if we look down in the geometry spreadsheet, you can see that the color position here is just the same as the py position. And then now that we've saved that attribute explicitly, we can come down to color type, choose ramp from attribute, and then the attribute that we want to choose we've already defined as color pos. And then we can set, if this doesn't appear, it's just this little arrow here, set this to constant, and then you can see as we move this around we're changing exactly at what height these dots will be coloured white. I'm just going to change this to something a bit more visible or a bit more different from each other. That looks pretty different, so you can easily see that these are two different colours. However, as we play this animation, you can see that those green dots, the colour information changes because this position value, or if you look down here, it's updating with the actual animation. But what we really want is for this position to only reference the first frame. So what we can do is drop down a time shift, delete this channel so that the time shift is basically only getting the information from the first frame, so anything after this is just going to be based on the first frame. So that actually means that the animation no longer plays, but if you can just trust me for a second, this doesn't really matter, because the way that we finish the rest of this, it doesn't depend on this node for the actual animation data. So accepting that this is fine for now, we can move on to our POP network. And the POP network is a particle solver within Houdini. And the way that it works is that it has, well, this is the default setup. This thing on the left is this. I think this is the initial, so the pre-solver stuff, but we're not going to use that because we don't need to pre-solve anything. This I don't like using because it's just a bit different from the way that you normally work in Houdini, so you can get rid of that. But what this first panel does here is that this defines what geometry is being fed in, or what points are being fed in, and the emission type that you can see is it's set to scatter on surfaces. However, we're not inputting a surface into the POPNet, we're inputting points. So what we can do is select all points, and then that's just the geometry that we want, the points geometry. And the other thing that we want to do is in this birth tab here, this is defining on which frames to actually birth that geometry that we're defining. So I don't want it to spawn the same geometry on every frame. I only want this to happen on the first frame, so we can put this expression in here to make that happen. So if we go out here, we should see that this is now passing through that geometry, but again still not doing anything because we haven't yet told the solver what we actually want to do with these particles. And there's a few different things you can do, but the one that I ended up using for this for this animation is pop grains. And pop grains is kind of like sand, or I don't know, like water molecules repelling each other. So pop grains, what it'll do is that for each of these particles, it will search the area for the closest ones and push them away from them. Now, an important thing that I've forgotten to do is in the scatter node, what pop grains relies on is a certain scale to be associated with these particles so that it knows how much to push particles away. And the way that we can add that information is going into the scatter node, output attributes, output radius attribute, and that's going to output a p-scale attribute. And then that just gets tagged on to the particles here. So we can then dive back into pop grains, and I changed the constraint iterations to 100. I changed the scale kinetic to 5, and I think that's all that I changed for this. So if we go back out of this, we can see that the pop grains is now doing its thing of repelling these particles from each other. With lipids, we want them to be repelling each other, but we don't want them firing off like this, because it will no longer look like a membrane. So this is where we can add in our own custom function by dropping down a POP VOP. And maybe I'll just switch to my tablet for this part. Okay, so if we take this white line to be our base mesh, what we've done on the first frame is we've scattered points onto this mesh, and then what our pop grain solver is doing is giving these particles a certain velocity, because it's trying to push these particles away from each other. If we focus on this central point, and let's say it's got a velocity vector like this, just get rid of these, then we can see this velocity is going to result in the particle moving away from the surface. Now, one approach that we could use is to basically break this vector into its two component vectors, where one of them follows the tangent of the surface. So the tangent of the surface just would be something something like this, and therefore we could, instead of using this, we could update the vector to be something vector tangent, and that could be an approach that works. However, one issue with that is that you do build up an error here. Every time you calculate the tangent vector, there'll be some distance between your new point and the base mesh that you're wanting to follow. And in fact, this is the way that I approached it first, but I ended up correcting for that error by just projecting down onto the surface. But by projecting down onto the surface, it means that you don't really even need to calculate this first vector here. So instead, the approach that I'm going to show you is simply, we can use Houdini to find what the closest point on the mesh is, and then simply move that point to there. And in that way, you're still getting movement from the pop grains. And while this won't be the most accurate kind of movement, it works, and it's the simplest way. So I'll show you how to do that in Houdini. Okay, so if we jump into our POP VOP, then what we want to do first is find what the closest point on our base mesh is, and we can achieve that by using an XY distance node, because what an XYZ distance node does is it takes the position of your particle or your point, and you can put in some base mesh here. That's what this input is, and then it compares the base mesh to your position, and then it finds the distance to the closest point on that mesh, and that's what that distance output would be. But it also outputs from that base mesh the primitive which is closest, and also the UV coordinates on that primitive that give you the closest point to your position. So we already have the position of our particle, but what we need to get is the base mesh. So the way that we do that is if we just go up a layer and go up another layer, what we can do is we can get our base mesh feed this into our second input on the POPnet. Click on our POP VOP and go to Inputs. And I'm just going to use the input 2 and click Second Context Geometry. So that second context geometry is referring to this second dot here on the inputs. And I've just chosen input 2 just to kind of be consistent of it's a second input, so we can just use a second input here. So by selecting this is passing the second context geometry within the POP VOP, and we can access that as the operational input 2 here. So we can just attach that to the input. So this is our base mesh. This is our particle point and primitive attribute. Yes, okay, so it's primitive attribute that we want to drop down here. And what this does is we can pass on the primitive number that's been identified as the closest primitive. We can give it also the UV coordinates on that primitive, and we can just tell it that the actual geometry is the input 2 as well. So that's, just to make that obvious, that up input is going to here and also to here. And then what we can do here, we choose the output that we want. And what we want is the position in space of that closest point on the mesh. And that is kind of it. That's what we want. So we can plug that position output and we can define that as the new position of our points on our geometry, and you might have seen it there, but you can suddenly see that that's snapping to the geometry. So if we go out of this, we can just rename this as move, or maybe let's call it project particles to base mesh, so that we know what that's doing. And let's take a look at what that looks like. I will just highlight the base mesh as well so that we can see whether or not it's sticking to it, and you can see that it is following the mesh. What you can sort of see, maybe, I don't know, it's probably easier to zoom out a little bit. You can see that there's sort of gaps in between the particles here, and these particles are kind of shooting out a bit too quickly. This doesn't look very good. So what we can add to sort that out is go back into the POPnet. We can add a pop drag. I think I set this to 2 in the end, but that will just apply drag force to the velocity and slow it down a little bit, hopefully. So let's see what that looks like. Yeah, that's looking a lot nicer. Let's drag all the way to the end and then just play that through. There you go. We don't have that crazy behavior going on where things are shooting out anymore. So the next thing I'm going to do is set up a copy to points. And then I'm going to instance some lipids on there. So the way, I mean, this is very low resolution lipid. I've just extended the box to this length here, 4.2. I think I've left everything else the same. I don't need that. I think I can just put 1.67 here. Yeah, so let's get rid of that lipid. This is what I want to copy to my points. So here we go. We've got some lipids copied onto the points. However, you'll notice, well, I mean, this looks actually really cool, but it doesn't make any sense for what we want. You'll notice that the lipids aren't actually aligned. So to update the normals of these points, I'm going to go into our POPnet. I'm going to just copy and paste this POP VOP that we made here, and plonk it in there, because it's very similar. It's a very similar setup to what we did in this, but instead of position data, the attribute that we want to get out is the normal, and feed that into our normals. Now we'll have a look at how that looks, and that seems to have done the trick. Okay, so our lipids now are lining up. Excuse me, I've got a bit of a sore throat. Are now lining up with the normals, which is looking really good. So we can we can sort of just select out some of these points here just to get the cross section. The way that I've done that is to define an x coordinate cutoff. I'm using a channel value. If you want to do that, once you've typed that in, just make sure to press this to get that x cutoff value here, and you can see that that's what that does. And then here we have an if statement. If the position of x is greater than our x cutoff value, then we're just removing those points. So go ahead and copy that in if a cross section is something that you want. Yeah, I think the final thing that we really need to do is this step here, and I'm just going to have to copy and paste this because I can't really remember what it was that I did here. I mean, the point of this is to just give these lipids a bit of a rotation, because at the moment they're all sort of aligned in a very similar way, but I want to add some random rotation to it. So I won't make this from scratch, just because like I said, I can't I can't remember exactly what I did. But let's go through this together. I think the main crux of what I'm doing is using a quaternion, which is a way of using the normals of a point. You're rotating around the normal of these points, and that's what your axis is here. You just feed it straight from the normal. So that's the axis to rotate around, and then you're feeding in at the top an angle that you want to rotate by. And how I've done it here is to drop down a random node, and the seed that I'm using for that is the point number. And then what I'm doing is, well, I guess I'm multiplying by approximately 2 pi. As you can see, if I put that to 0 and shift that around, you get random rotation of each of those points. Let me just undo that. And then finally, to output this quaternion value, I have named it ROT, or this is the default rotation. I guess it must be the default because I think this is interpreting that ROT value. So hopefully when you do this will work for you. There is one thing that I haven't showed you, which is based around, if we zoom in here, one thing that I don't like about this is that these lipids get a little bit too close before they start to merge. And one kind of solution that I've found to address this is just to add in a few more nodes up here. So if we add in a VDB reshape and plonk that before our VDB smooth, what we're doing to the mesh is we're basically expanding it a bit here, okay? But because we're expanding it, that does mean that our vesicle is bigger. So we can effectively undo this expansion by copying this underneath, and instead of dilate, we can erode it, and that kind of just brings it, if we erode it by the same amount, then that should sort of preserve roughly the size that we want. And what I found works best is using 5th order. For this particular example, I've set it at this value. What you can do here is copy this parameter, because we want it to be the same here, and just paste in that relative offset. I also want this as a 5th order. And in that way, that creates quite a nice looking blob. If we go to the end, we'll just have to resimulate this. What you can see is that there's no longer as much of overlap before it starts to merge. So yeah, that is pretty much it. If you've got any questions, post them in the comments. If you've got any improvements to suggest, please do comment that as well. This does, as with anything that you're simulating in Houdini, it does take a lot of time just to kind of get these parameters right. But obviously I've done this for you. But if you're doing your own project, you might find that you want slightly different behaviors. One thing that I'm thinking of doing next is adding in a bit of Brownian motion to these lipids, just so that we can sort of see some sort of diffusion going on, some sort of intermingling of these colours. Another thing that somebody suggested to me was, you'll notice that there's some flickering that goes on at the front here. That's because of we're blasting out lipids that are beyond this point here. But you could do this in another way, of kind of similar to what we did here with the time shift. You could get the positions at the first time frame and only show the ones that are on this side of the x-axis at frame 1. However, I did try that, and some of the lipids kind of spill out into the front because it's a simulation, so that wasn't the neatest way of doing it. But I suppose one way you could do is maybe, I don't know, applying a bit of a force here, or well, actually no, the simplest way probably is just to do a boolean on your mesh here. Although if you do that, you will get these edge artifacts that you get at the edge of this. So that's a bit of an open problem. I'll have a think about that, and probably never make a video about it, but maybe you can have a go at that as well. But thanks for watching. If you made it to the end, I'm impressed, because I have been rambling on for a long time. But thanks, all the best, cheers.